everybody. I'm Amog. Today I'm joined by Josh, and we are AP Tutor. And today we're going to be doing a lesson on 2D kinematics for all you AP Physics 1 students out there. And if you guys haven't already, make sure you do go back and watch our 1D kinematics video, because that contains a lot of useful information and a lot of useful foundations which will help you in this next video. So if you guys have already gone ahead and watched that, we'll get started on today's lesson. If you remember from the last 1D kinematics video, Josh talked about scalars and vectors. And if you guys remember, scalars have magnitude and vectors have both magnitude and direction. So whereas the scalar is just going from point A to point B, as we did in one-dimensional kinematics, whereas we don't really care about which direction it's going in, with a vector, you can see that we might have a vector going from A to C, which is going to the right, and then we might have another vector going from C to B, which is up. But we do care about the fact that it's going to the right and it's going up. And as you can see, we can add together vectors, like in both situations here, but we'll focus on the right one. We have a vector going from X to Y, then we have a vector going from Y to Z. But instead of having to think about those two individual vectors, we can just think about the resultant vector, X to Z, which we can find by putting the head of the first vector and the tail of the second vector together to get our resultant vector. Now, it is a bit difficult to straight up use a vector in its own situation, because you might have one vector in one direction and then another one going in another direction altogether. So it's nice to break it down using a system that we already know, and that's going to be our coordinate system. So we might have a vector D, which in this case is going to be our displacement, and that's going up and to the right. But instead of just thinking of it as up and to the right, we can break this down into our two components, which is to the right and up. And in our coordinate system, that's going to be the vertical and horizontal components, which are X and Y. So we know that this is essentially a right triangle, so we can write that out. And we also will know our angle here. And since we know that this is a right triangle and we know that we're looking for the sides of it, we can write down our familiar trigonometric formula. So sine theta equals the opposite over the hypotenuse. And now in this case, the hypotenuse is just going to be D, and the opposite is just going to be Y. And since we realize that this has all the quantities that we need to figure out the Y, we can just rewrite this equation as Y equals D sine theta. And that's essentially how we figure out the Y component of our first vector. And to figure out the X component, we can write out our next trigonometric formula. Cosine theta equals adjacent over hypotenuse. And once again, we know that the hypotenuse is just the original vector, and we know that A is X in this scenario. So we can write out the formula for our X vector as X equals D cosine theta. Now, more often than not, you'll be asked to find the initial velocity. You'll be given the initial velocity of a projectile and then asked to do further calculations. But as I mentioned before, you're going to want to have to break this down into multiple components to make your calculations easier. In this case, it's going to be a horizontal component, how the projectile is going horizontally and how the projectile is going vertically. So we can use our similar formulas, except this time it's just going to be dx on the bottom and dy on the top. We can replace in our y equals d sine theta, we want to find dy, and this is going to equal v naught sine theta, which is given. And same thing with x, that's just going to end up being vx equals v naught sine theta, cosine theta, sorry. And as you can see from here, we're able to break down just an initial velocity as well as a displacement into its individual components to calculate them using a coordinate system we're familiar with. So this kind of vector addition, this kind of vector breakdown can apply to anything. It's not necessarily always going to be just a d sine theta or a d cosine theta, or even a v naught sine theta or cosine theta, because it just depends on what your original vector is and what you're breaking it down into. And as I mentioned before, it might be a good idea to once again think about the idea of vector addition, because we might be given, say, a person walking a certain distance in this direction, but then he might change direction and we're going to be asked to find final displacement. So what you're going to want to do in this situation is not try and ponder how you're going to make them both in the same angle. Instead, just break them down to their individual components. You have your vector xy, break it down into its x component and its y component. Break your vector yz down into its x component and y component. And since at that point, you just have one-dimensional like vector components, you can add those components together, the x and y component, and then you can recreate your resultant vector by turning them into vectors again. Now we're going to apply this to two-dimensional kinematics using the idea of projectile motion. So now we're going to apply our knowledge of vectors to two-dimensional motion, which is what comes on the AP Physics exam. So you can see here we have a parabolic path, which is the path that a projectile usually takes in the conditions that are present on the AP Physics 1 exam. And so you can see these colored arrows, and what these arrows represent is the vertical and horizontal components of the particle's velocity at these different times. So the blue arrows, which are pointing to the right, represent the horizontal velocity, and the red arrows, which are pointing vertically, represent the vertical velocity. Now you can see that the blue arrows are consistent in length the entire time, whereas the red arrows start vertically up, then slowly get smaller and eventually turn downwards. Now, why this is because we know that there's a vertical acceleration due to gravity, and in this situation, that is going to be downward since we're throwing the projectile upward. We're throwing the projectile upward, and gravity is acting downward. So we're going to assume, and it's always good to set a coordinate frame of reference beforehand. We're going to say that upward is positive and downward is negative. If you don't set this beforehand, then you might switch up your positives and negatives in your equations, and either you might mess up your answer or the AP grader might not understand exactly what you're writing. So always set this whenever you're working with projectile problems. Now, it makes sense since the particle starts vertically, and since there's a negative acceleration, which is downwards, it eventually turns to a downwards velocity. However, we know that there's no horizontal acceleration necessarily, and since we can assume that there's no resistance, the particle's horizontal velocity always stays the same. And this is very useful because then we know that in horizontal motion, the particle's acceleration is 0. If we think back to our big 5 kinematics equations, which we essentially use for all of kinematics, this essentially restricts us to our equation such that we know that the final velocity of the particle is going to be the same as the initial, which means the particle is going to have a constant velocity the entire time. And therefore, the only equation we really need to know is delta x equals v bar t, which will help us figure out the distance the particle travels in a certain period of time. However, we don't have any more horizontal equations to figure out the time, so this is where we turn to our vertical equation. Now, vertically, there is going to be an acceleration, and this is going to be downward, which is gravity. We know, as we define, that this is going to be negative, so the y acceleration is just going to be negative g. Now, we can find the vertical velocities using a similar equation as horizontal velocity. Vf equals v naught y, and we should probably put v naught x here so that we know to differentiate between the initial x velocity and the initial y velocity, that there's going to be an acceleration in the vertical component. And since we know it's going to be negative, we'll write Vf equals v naught y minus gt. Now, the final thing we'll want to find is the y position of the particle at any point in time. And this can also be used to find the maximum height, which we'll come to in a second. So we can just write this out using delta x equals v naught t plus 1/2 at squared, except we're going to change this to y motion. So we're going to have y equals y naught, which is the initial position as compared to the final position that you think that you want the particle to land on, plus the initial y velocity times t, minus 1/2 times the gravitational acceleration g times time squared. Now, essentially, these are the only equations you're really going to be using for projectile motion in terms of horizontal and vertical components. However, we can essentially use these equations to derive newer equations to help us calculate quantities quicker. So the first of these is we're going to calculate an equation for the maximum height of the projectile. So we know that the vertical velocity of the particle turns from positive to negative at some point, and for that to happen, it must be 0 at a certain point. That point is the peak of the particle's motion. And so we're often going to be asked on the AP exam during a projectile motion problem, what is the maximum height? So the first thing we're going to need to do to find that equation is we're going to write down that we know that the final velocity at the height is just going to be 0. Then we can go back to our equation, Vy equals V naught y minus Gt. And we can simply plug in our value for Vy. And after this, since we know that it's 0, we can just rearrange and simplify it to get a value for time, which is just the initial y velocity over the gravitational acceleration. Now, this is a value for time, but what we want to find is the maximum height of the projectile. Now, we know our equation for vertical displacement, which is y equals y naught plus v naught yt minus 1/2 times the gravitational acceleration times time squared. But since we're starting from our y level of 0, which is what we normally want to make it, we can just cancel out our y naught squared. And so we're just left with y equals v naught yt minus 1/2 gt squared. And now we're left with this, but remember, we calculated a value for time here, so we can plug this into this equation. And I'm going to do that down here for a bit more room. And we can replace y with h, since h is going to be our the variable for our maximum height. And if we write it out, we get v naught y times v naught y over g. So we're plugging it in for the first t in v naught t minus 1/2 times g, and then we're going to plug in v naught y over g for the next t squared. Now we can simplify this out to where we get h equals v naught y squared over g, because the v naught and the v naught multiplied together. And then we also, over here, we get v naught y squared over g squared, but then it's times g, so it just becomes 1/2 v naught squared over g. And then we can simplify this out since these two are the same term, and we get that the equation for the maximum height of a projectile is v naught y squared over 2g. Now, don't just memorize this formula, because that won't be acceptable on an AP exam. You're going to want to understand how to derive it, so that way when the time comes, it'll be much quicker for you guys to be able to do this. So the next equation we're going to derive is going to be the range equation. So the range is the horizontal distance that a particle covers over a certain period of time. And for this specific equation that we're going to be deriving, it's important to remember that in order to use this, the particle has to start on a certain y level, in this case y equals 0, but it has to end on the exact same y level, which is y equals 0. If it lands higher or lower than that, this equation will not work, and you guys will mess up your answer. So do not derive it this way if that's what the question is asking. So we're going to start by figuring out our total flight time of the projectile. And so that's just going to be twice the time it takes to go from its maximum height all the way back down. And that's, as you can see, that's why it's important it ends up on the same level, or else it won't be twice the same time it takes to go up. And if you remember from the prior step, the maximum height equation, we calculated that the time it takes to go to its maximum height is v naught y over g. So we can write out that the time equals 2 times v naught y over g. Next, we can go to our horizontal equation, which is delta x equals v naught x times t. And here it's important to remember the difference between v naught x and v naught y, which you'll see in a second. We can replace t with what we calculated. T equals v naught y over g. So we're going to get 2 times v naught x times v naught y over g. Now, we're going to bring out our original equations for how we can calculate v naught x from the initial velocity. And if you remember, v naught x is just v naught cosine theta, and v naught y is v naught sine theta. So we can replace delta x with r, which stands for range, similar to how we replaced y with h for the maximum height. And so we're going to get y equals 2 times v naught cosine theta times v naught times sine theta, all over g. Now, we can simplify some things out here, and we're going to get that the range is equal to 2 times v naught squared sine theta cosine theta over g. Now, we could leave it here, but it's important to remember one of our trigonometric identities, and that's that sine 2 theta equals 2 sine theta cosine theta. And we can see that we have that here in this range equation, 2 times sine theta times cosine theta. So we can rewrite the range as v naught squared sine 2 theta over g. And that's our range equation. So we'll go back to our 2D projectile motion slide. These are the equations that you're going to be using to calculate your vertical and horizontal components of motion. And we learned how to derive 2 individual equations, which are specialized for finding the maximum height and for finding the range, which works when the particle starts and ends on the same y level. Now we're going to learn how to apply some of these equations and use them in problems, and Josh is going to take you through some of those.
All right, so for those of you that don't know me, my name is Josh, and I'm the other half of this YouTube channel. And I'm going to take you through some application-based practice that is the same type of question you'll see on the AP exam related to this topic. So let's get started. Remember, you can read this question, and if you feel so inspired, you can try to figure this out on your own, and then come back later on in the video. We are going to show the answers to these. So if you feel inspired, take it over from here. But let's get into it. Ryan is playing striker at his rec soccer game and is ready to shoot. He kicks the soccer ball from rest to 22 meters per second at 35 degrees above the horizontal. Top of the goal is 8 meters high and it's 27 meters away from where he kicked it straight on. So as you can see from this problem, the College Board loves to overload you with numbers and get your mind really spinning. And you just gotta read it twice and then break it down. So let's figure out what's going on. So we have Ryan. This is a lovely guy, Ryan. Sure, he's popular. And this is my lovely drawing of a soccer ball. So he kicks it from rest and it goes like that at 22 meters per second. And this is 35 degrees. And the goal is somewhere over here. It's 8 meters high, 27 meters from where he kicked it. So let's go with something like that. But now this isn't really asking about any of this. It's asking if Ryan kicks the ball for 0.2 seconds, what is the acceleration of the ball in that time? Well, it's kind of a trick question. It's easier than it looks. We know that acceleration is equal to change in velocity over time. And since our initial velocity starts from rest, that means starts without not moving, it's not moving. So that's just equal to VF over T. Now we can plug in our numbers here. And finally, we get a pretty fast number, 110 meters per second squared. Now, a lot of you might think, all right, we have our number, we're done. But remember, AP graders are tricky. You forgot the vector sign. Vector sign means you did a direction too. Sometimes they'll ask for magnitude, but this time they didn't. So now you gotta think about it. So it starts from rest. It starts from 0. 0 doesn't have a direction. 0 isn't going anywhere. You can't go 0 meters per second west. That doesn't make sense, right? So if you're going in a direction 35 degrees above the horizontal and you start from 0, your change in velocity, your change in direction there would be at 35 degrees above the horizontal. You can just box in your answer to let them know that it's there. Now let's go on to the next part. So how long does the ball take to reach the plane of the goal? So what do we need to figure this out? We know that the ball starts, nice ball starts from rest, and then it goes like so with initial velocity 22. And then the goal looks something like that. This is the goal. And distance from here, remember, it's 27 meters away. So what does it mean to reach the plane of the goal? So the goal is this entire big net right here. The plane of the goal is this little, it's basically the front of the goal, the front edge of the goal that's defined by this top post and these side posts. So how do we figure this out? So how long does the ball take? So they're asking for a time to reach the plane of the goal. So remember, because we're only dealing horizontally, we don't care if it goes up or it goes down, if it makes it in or not, at least for this one. We only care about horizontal. So we know it travels 27 meters. And we know in projectile motion, as Amog said, horizontal velocity stays constant. So we can use our simple delta x equals v bar t. But are we done? Well, not yet. What is v bar? V bar, since vertical velocity is changing, the only thing that's staying constant is vx. So let's find vx first. And let's plug in our numbers. And finally, we end up with 18.0 meters per second. This could be just to the right. Though I think they're writing in 2 significant digits, so you don't really need the 0 if you don't want to. All right, so now we know this, and we're solving for time. So let's just plug in and solve. And when you're done, you will get a value of 1.5 seconds if you did it right. And that's the answer here. On part 3, here's the application. Does the ball make it in? Assuming the top goal post has negligible thickness, how close was the ball from missing? So this is the kind of thing AP graders are going to ask a lot. It makes you think a little. You can't just plug in numbers and figure out the answer. You have to think about it. So let's imagine our ball. It goes like this, and here's the goal. So from here, it looks like it's going to go in, but we're trying to think about this. Is the ball going to go up and miss the goal? Is the ball going to go in or make it in? So how do we figure that out? Now we have to actually know the vertical velocity at the point of the plane. So at this spot, is it above the goalpost or is it below the goalpost? And we can figure that out by first realizing that the vertical velocity is changing due to gravity. So we want to know how high it is, right? So we can use the equation delta y is equal to v naught y times t, well, minus in this case, minus 1/2 gt squared. And we know everything here except for v naught y, which we need. We know that vy is equal to v naught sine theta. Remember, that's the thing that Moog was talking about. So let's plug in right now and figure this out. And you should get 13 meters per second. This is positive right now, so that's going to be up. So now we can simply plug our numbers in. We know time to be 1.5 seconds, right? From the last problem. Remember, time is the same in both dimensions. If I drop something, it's going to hit the ground at the same time. If I throw something, it's going to hit the ground at the same time in the y direction and the x direction. So t is going to be the same. So now let's plug our stuff in and figure out delta y, which we want. All right, so if you plug all of this in, then you will get 8.5 meters. So this is delta y. So you know the change in y is equal to y minus the initial y. So if we look at it here, and we're starting from ground level, so that is y equals 0. So this doesn't matter anymore. And delta y equals y. So y is equal to 8.5 meters. But that's not what they're asking. They're asking, does the ball make it in? And for that, we have to extract some info from the problem. We know the goal is 8 meters high. So if the ball right now is 8.5 meters above the ground, and the goal is only 8 meters above the ground, oh no, I guess Ryan missed the shot today. So he does not make it into the goal. But we're not done yet. How close was the ball from missing? Well, that's not that hard. We know that the ball is at 8.5 meters, and the goal, the top of the goal, was at 8 meters. So we simply subtract them to find how far he was. So 8.5 minus 8 meters is equal to 0.5. Oh, he was so close. He was 0.5 meters off. Now let's go to the last part of this question. So how fast is the ball moving when it reaches the plane of the goal? So remember, we know what the time is, and we know our initial x and y velocities. So this shouldn't actually be that difficult to figure out. Let's talk about the x component first. So we know that there's no acceleration in the x direction. So our initial v naught for x is going to be equal to our final. Because if there's no acceleration, that means velocity isn't changing. Remember, this is the kind of conceptual stuff you have to know. So what is v naught x equal to? Let's go back and figure it out. It was 18 meters per second, right? So 18 meters per second. Let's find Vy now. But here's the thing. We know that there's an acceleration going on in this side. It's not as easy as this. So we can rewrite this as Vy, it's really tongue-tied here. V naught y minus gt. And we know what this is. And we know what g is. And t we can use from 1.5 seconds as we learned here. Remember, it goes at the same time. They're asking here the plane of the goal, and they're asking here also the plane of the goal. So we can figure this out, v naught y and gt, so we can simply plug in and solve. And finally, you should get negative 2.1 meters per second. So now what does this mean? So since this number is positive, we know that positive is up in this case, and negative is down. So this means that since this number is positive, well, this is in the x direction. This is positive. Remember, x is only left and right. So we're going to the right. And since this is negative, we are going down. So let's construct a vector. So this is the usefulness of vectors. You can add them, you can subtract them, but they're not asking for how fast in any direction. They're asking how fast completely. So for that, we have to put these two components together into one big vector. So we know this is going to the right. So let's draw our rightward x component. So this is 18 meters per second to the right. This is this. And we're going down. 2.1 meters per second down. So we can draw a vector from the here to there. Remember, this looks just like the kind of vectors that Amog showed you, like this. This is just the application of that. So now we want to find this. How fast are you going? So let's think about this. This is x and this is y, so they're perpendicular. This is kind of looks like a right triangle, right? So we can use a squared plus b squared equals c squared to figure this one out. And simply plug in the numbers and we can get b. So we know that bx squared plus by squared is equal to b squared. And we want v. So now let's plug in our numbers and solve. Yeah, I know I forgot the negative sign there, but when you square it, it's not important. So finally, you should get a final answer of 18.1 meters per second. But here's what you should notice out of this. Notice that this is not really that far away from 18. That's because the 18 is not really drawn to scale. The real triangle would look more like that. The horizontal component is so much bigger than the vertical component that this answer is really close to that. But how fast is the ball moving when it reaches the plane of the goal? That is 18.1 meters per second. And that's all for this one. All right, here's our last and final problem. So if you read through it, you'll see there are no numbers besides these over here. But this is what's called a symbolic derivation, where they're going to ask you to solve for numbers without giving you the numbers. So they're asking you to solve for, like, they'll give you this and that, and ask you to solve for t. So let's figure this out. A ball is shot off a table horizontally with initial velocity v. Table is at a height h above the ground and air resistance is negligible. In terms of the given quantities and fundamental constants, solve for the problem, for the following. So let's start with number one. Remember, if you think you can handle any of these problems from here, don't let me do it. Try it on your own. So we're trying to figure out t here, right? So it says in terms of the given quantities and fundamental constants. Fundamental constants are stuff like g, stuff that everyone knows what it is. It stays the same. H and v are what we're allowed to use here. Try to solve for t, the time the ball takes to hit the ground. So we know that what delta y is. That's h. We know initial velocity, v naught y. Remember, this is launched horizontally, which means all of this velocity is x. This is all in the x direction. They leave nothing for y. So v naught y is equal to 0. Trying to solve for t. So what's t? And we know the acceleration, as always, is equal to g meters per second squared. Could be negative depending on how you're thinking about this, but since you're following a distance h, we could either call them both negative or both positive. I prefer to call them both positive. I like to work in positives. Don't be pessimistic, work in positives. So let's figure out our equation here. We know that delta y equals v naught yt plus 1/2 gt squared. This is positive now since this number is positive. But we know this is 0, so we can just cancel out this whole term. And that just boils down to this. So let's plug in and figure it out. Not really much to plug in there, but now we can isolate and solve for time. Remember, you can't have negative time, so you wouldn't leave the plus or minus on the end of the square root. You just leave something like that. Number 2, we're trying to solve for x, the horizontal distance, or the range the ball ends up from the table. Here's the thing, you cannot use the range equation here though, because you are starting on a table. A table has a height, h, and you're ending below that. So since you're not starting and ending at the same spot, you can't use the range equation. We have to figure this out on our own. So let's figure out what we know. We want to find delta x. We know our initial in the x direction, that's v. And we know acceleration is equal to 0. So that means Vx is going to be equal to v no matter what. This velocity in the x direction does not change at all. So that means we can simply use delta x equals v bar t. But you might ask, what is t? Well, you gotta remember this. It's always the same in both dimensions. Both directions, x and y, time is always gonna be the same. So we can simply take what we know from the first part and put it in here. And that's literally all you have to do for this one. Now let's go to the next one. So we have a little addition here. Now the ball is shot at an angle of 45 degrees. The maximum height of its trajectory is y. So this is not h, this is different. So we have another one called y. So, in the previous part of the problem, you're shot off like this. Now if this is your table, T for table, you're shot off like that at an angle. So now your angle is 45 degrees. So now use the range equation to find the range of the ball. So when they ask for the range equation specifically, that means you're going to want to find the distance that the ball travels from here. If there was another imaginary table with the same height, what would be this distance right here? Again, in this kind of problem, you assume it doesn't hit the ground. So we know what the range equation is. V naught squared sine 2 theta over g. So in a case like this, you can literally just plug in. We know sine 90 is 1, so that won't matter. And that's our answer. Now let's go to the last part. Now, if it is now launched at 90 degrees, find its new maximum height in terms of y. So College Board, a lot of the time what they do with these symbolic derivations and questions like this is they ask you to compare two things. So you have to find its new maximum height, but in terms of y. So it'd be something times y, or something minus y, or something y minus something. It's always going to be concerning y. That means we have to figure out what y is. And here's what the equation Amog derived for us up here will help us. We know that the maximum height of any projectile is equal to v naught in the y direction squared over 2g. So let's write that again here. So in this kind of situation, we could set this as h initial, we could set this as h final. So h final, what would that be equal to? So that would be equal to v naught y squared over 2g. So this is a different v naught y though, since we're launching in a different direction. Let's figure out. V naught y is equal to v naught times sine theta, right? This is from our original equation up there. So now looking at this, we know v naught is just equal to v. So in the first instance, when it's y, that would be sine 90. Sorry, I messed that up. Sine 45. So we can just leave it there. You don't really need to know what sine 45 is. And here, let's know that v naught y in this instance is equal to v times sine 90. It's just equal to v, because it makes sense. You're launching straight up. So there's no x component here. 90 degrees is just up. What is that? All right, so now we got to figure this out, right? We simply, because g stays constant, so g is the same, you have to figure out its new value in terms of y. So we know that, let's extend this page a little bit. Initially, this is its initial one. So only v naught y is changing. So let's figure out what, in the original case with y, v naught y is changing. So v sine 45 squared, that's equal to v squared times sine 45 squared. In this case, it's just equal to v squared. So what is sine squared of 45? Because if this and that are the same. So this is the only thing that's making them different. So we can simply put that into your calculator, since you're allowed to have calculators on the AP exam. Solve that and you get it's equal to 1/2 v squared. Sine 45 is equal to 1/2. So if this, since we know these are the same, if this is v squared and this is 1/2 v squared, remember this can tell you something about y. This can also tell you something about y. This symbol alpha just means proportional. So if you know that this is v squared and this is 1/2 v squared, that means that the new y is equal to 2 times the old y. Because this is 1/2 and this is 1. As you can think about it, this is 1 here. So that means your y new is equal to 2y. And that's your answer. Your new maximum height is equal to 2 times your original maximum height in this kind of problem. So both of these problems are both questions that they often ask, College Board asks on the AP Physics 1 exam. So I hope this lesson helped you guys. Please give it a thumbs up. And if you like what you see, subscribe to our channel and check out our other content. And I think my name is Josh, and I'm joined with the Moog, and we are signing off for today.